Hey programmers, welcome back. Right now I want to go over the approach for this tree pathfinder problem. So this is going to be a pretty interesting problem. So basically what we want to do is, given a binary tree, we want to basically find a target. But this time around, instead of just returning a simple Boolean, if we are able to find the target within the tree, we want to return the path to that target, right? And so what we want to do is return an array representing the path to that target from the root. In other words, you can definitely find the E within the tree, and we want to return an array containing ABE, right? Starting at the root, what are all of the nodes we'll have to travel to get to the target? So let's say in another example, our target was C. C is definitely found within the tree, and the path we should return is just this path, right, of AC. Cool. A final scenario we should probably think about is, what if we had a target that was not found? In other words, what if our target was a letter like P? P is nowhere to be found in the nodes of this tree, so in that scenario, we just want to return null, right? So that'll be an edge case that we have to handle. All right, so looking at this problem, it may seem like a tough one, but hopefully you're able to recognize some patterns that we've seen before, right? So a previous problem that I'm reminded of here would be the tree includes problem. We just have to return Boolean, right? True or false is the target within the tree. This time we just want to return more information, right? That is, if it's found, I return an array representing the path to where I can find it. But if it's not found, instead of returning false, I return null here, right? So hopefully you're doing these problems in order. If you haven't done that tree includes problem yet, I recommend you do that one first. But how can I start attacking this one? Since in this problem, they want us to basically return a path, typically I find the depth first recursive code the best way to solve it. And so I'll go ahead and trace through how that can work in this approach video. And so we'll stay committed to solving this one recursively with a depth first. And let's say we were stepping through it as if we were looking for a target of E, right? So what I want to do is, of course, begin with my base case. And the most important thing I need to establish in my base case is a consistent type, right? So I know in general, right, this problem asks us to return an array of some values. So even my base case should return an array of some values, right? It probably will just be a small array. And so let's say we had a scenario where we were at a node that contains our target. In other words, we have a match, right? If I have a match, that is, if I run into a node whose value is E, then I think that node can immediately return an array containing the value E, right? And that would just be consistent with the shape of the problem. So I'm just going to plug in this visually right where I find the E node, right? So I'm saying that, all right, when I make a recursive call on that E node, I should treat that as a base case and just automatically return an array filled with the value or character E. Nice. And now we're going to need another scenario, right? That matching base case kind of sounds like the affirmative, meaning we did find the thing we're looking for. But what about the opposite scenario? What if we don't find what we're looking for? Well, we know we basically hit a dead end in our tree, and there are going to be many dead ends, but we hit a dead end in the tree whenever we call upon a null node, right? And we've seen this pattern a few times before, right? So just visually, although it's not, going to be something special we have to account for, but at least in our drawing, I'm going to explicitly draw what our null pointers would be. And they would look like this, right? Notice that I'm not going to actually draw any null pointers from the E node because I just said that it's its own base case, right? And it's going to return an array of E. Cool. So for all of these null nodes, they should return null, right? And what's the logic behind that? Well, I think about all of my base cases as if they're their own problems, right? So typically a null node, if you kind of interpret it as its own tree, a null node is the empty tree. And I know that the empty tree should always return null because you can't possibly find any target within the empty tree. And that's consistent with the problem. Cool. So now that we have some base cases laid out, how can we use these values to build up higher level solutions? So let's say we look at this D node, right? We're going to evaluate this depth first style. And what should this D node return? Well, if it looks at its values that it's receiving from its left and right, it's getting null, right? So if I get a null from my left, that means, all right, I did not find my target in the left subtree because my target's E, right? In the same way, if I get a null on the right, that means I did not find my target in the right subtree. So if I don't find my target in either of my subtrees and I don't contain it at all myself, right, because D is not equal to E, then this node can return null, meaning we cannot find a target at all within this subtree. Things get more interesting when we evaluate this B node, right? It's ready to compute. So if I root myself at this B node, right, so I have the perspective from the B node, On my left, I'm getting null, which means I didn't find anything in my left subtree. But along the right-hand side, I'm getting back an E, right? An array of E, which must mean that I found the E in my right subtree. And so what I'll do is I'm going to just drop the null on the left, and I'm going to prefer to just analyze the right value, right? And so I know that I need to incorporate this array of E into my final answer, but I need to add myself, right? Because I have to construct and return the full path. So I'm going to put the B value at the front of that array, right? And if I pause for a moment here, this seems logical because if I root myself at the B node, above it I have the return value of an array of B comma E. That represents the path I can take from this subtree to the E node. Cool. And we'll evaluate the rest of this. So at this F node over here, I have 2 nulls, which means I didn't find my target in either scenario. So this should just return null. And at the C node, same thing, null on left, null on right. So I didn't find anything. So this should also return null. And finally, at my top level root, I look at these 2 values, right? If I'm rooted at A, I have an array of BE on my left, which means I found something. But on my right, I have null, which means I didn't find something on my right. So I prefer the left-hand side here, right? But what I need to be sure to do is put my own value, because I'm the parent, into this path, adding it in the front. So ending up with ABE. And it's important that we get the correct order of things here. And logically, this return value of ABE is our top level answer, and it represents, of course, this path within the tree. Cool, so that seems pretty reasonable to code up, right? Something to watch out for when I code this one up is probably the fact that I'll need 2 base cases, right? I need to catch the scenario where I have a match, and I need to also catch the scenario where we have a null node and return null. Cool. That being said, what can we say about the complexity of this algorithm? Well, like always, we'll say n is the number of nodes. And I think if we do this the correct way, we should end up with a time complexity of O of n, right? Because we should just have n recursive calls, right? A call for every node within the tree. However, if we kind of don't do efficient operations, I can kind of imagine if we built the return array in a very inefficient way, we might end up with a larger time complexity. So what I'm arguing for right here is if we do this in the most efficient way possible, so this is kind of like a code detail, we should end up with an O of n runtime. Space complexity should also be O of n for the stack space, and I guess also the return value. So again, something that we'll have to stay super focused on is try to avoid slow and costly array construction, right? In other words, instead of creating and copying over a new array as I build up my solution up the tree, it would be better if I can keep a running array. Don't worry if that means nothing to you right now. You'll realize this when we code it up together in the walkthrough video. So I'll catch you there.